Have you ever looked at a massive bridge or a skyscraper that seems to just scrape the clouds and thought, how does that not just collapse? Well, the secret isn't just about using strong materials. It's about the brilliant science of bending stress. In this explainer, we're going to dive into how engineers master these incredible forces to literally build our world.
Right, so how do you do it? How do you build something that spans a huge river or reaches for the sky? This isn't just some textbook question. It's the real fundamental challenge that structural engineers have to solve every single day. And the answer? Well, it lies in understanding and controlling an enemy you can't even see.
So here's our game plan. First, we'll get to know this invisible enemy. Then, we're going to peek inside a bending beam to see what's really going on. After that, we'll learn the secret formula they use to calculate it all, and discover why a beam's shape is its ultimate superpower. And finally, we'll see how engineers put it all together to keep us safe.
Okay, so when you or I look at a steel beam in a building, it looks perfectly straight, totally solid. But here's the thing. Under any kind of load, every single beam bends. It might just be a tiny microscopic amount, but that little bend creates some seriously powerful forces inside the material itself. And this right here, this is probably the most important idea of all. You can pile a ton of weight on something, but it's not the weight, the load, that's the real villain. The thing that actually causes a failure is the internal stress that builds up inside. So an engineer's main job? It's to be a stress manager.
So what's really going on inside that beam when it starts to bend? Come on, let's zoom in way down to the microscopic level and take a look at the anatomy of a bend.
I want you to imagine the beam is made of millions of tiny little fibers, all lined up. As it bends down, what happens? The fibers at the very top get squeezed together. We call that compression. And at the exact same time, the fibers at the very bottom get pulled apart, and that's tension. It's this constant push and pull battle going on all at once.
Now, if the top is getting squeezed and the bottom is getting stretched, it kind of makes sense that somewhere in the middle, there has to be a place where, well, nothing is happening, right? And there is. It's called the neutral axis. You can think of it as the calm in the middle of the storm. It's one layer of that material that doesn't get squeezed or stretched at all. It has zero stress.
So this tells us something huge. The stress is not the same everywhere in the beam. It starts at zero, right there at the neutral axis, and then it just ramps up and up the farther you get from the middle. And where's the maximum stress? You guessed it, at the extreme top and bottom edges. Understanding this simple fact is the absolute key to smart, efficient design.
Okay, this is all great, but how do we put a number to this stress? How can we calculate it so we can actually control it? Well, engineers have this powerful and honestly pretty elegant tool called the flexure formula.
And this is it. It might look simple, but this little relationship is the secret code that lets engineers design everything from a bookshelf in your house to a massive suspension bridge. And know, for a fact, that it's gonna be safe.
All right, let's break it down. Sigma, that's our enemy. The stress we need to keep under control. M is the bending moment, which is basically the force trying to bend the beam. Y is simple. It's just how far you are from that calm, neutral center. And then there's I, the moment of inertia. Now this is the secret weapon. It's a score that tells you how good the beam's shape is at resisting the bend.
And that letter I brings us to maybe the biggest, most important takeaway from this whole explainer. To make something stronger, you don't just need more material, you need a smarter shape. Let's check out why. Think back to that stress diagram. All the material hanging out near the middle, near the neutral axis, well, it's kind of being lazy. It's carrying almost no stress at all. So if you're an engineer trying to be efficient, you're thinking, why am I wasting material and money on that lazy part of the beam?
So let's put it to the test. Look at these two beams. On the left, a solid square. On the right, that classic I-beam. Now, here's the picker. Let's say they're made with the exact same amount of steel. That means they have the same area, they weigh the same, and they cost the same. The only difference is the shape. So, which one do you think is stronger?
To figure that out, engineers use a really practical number called the section modulus, or Z for short. It basically takes that shape strength score, I, and combines it with the beam's height to give you one simple, easy-to-compare strength rating. All you got to remember is this. A higher Z is a stronger beam. Simple as that.
And boom! There's your answer. It's not even a contest. For the exact same amount of material and the same cost, the I-beam is dramatically stronger. Its Z-score is through the roof.
And now you know why, right? It takes that lazy material out of the middle and moves it to the top and bottom edges, exactly where the stress is highest. It's an absolute masterpiece of efficiency.
Okay, so let's put on our engineer hats for a minute. How do you use all this knowledge to actually pick the right beam for a job? It's a surprisingly straightforward 4-step process.
Okay, step 1. Calculate the load. You figure out the maximum bending moment, M, that the beam is ever going to have to deal with. Step 2. Know your material. You look up a value for, say, steel that tells you the maximum stress it can safely handle. Step 3. Find the strength you need. You just rearrange that formula to calculate the minimum section modulus, or Z, that you're going to need. And finally, step 4. You open up a steel catalog, find a beam with a Z value that's at least as big as the one you calculated, and you pick the lightest one, because lightest means cheapest. It's a perfect blend of safety and efficiency.
And that's the whole principle right there. It's not about brute force, just throwing more material at a problem. It's about smart, intelligent design. By understanding exactly where the stress is inside a beam, we can put material only where it's needed most. And what do we get? Structures that are stronger, lighter, and more cost-effective. It's a total win-win-win.
So we end right back where we started. But now, the next time you drive across a bridge or look up at a skyscraper, you'll know. You'll know the secret to its incredible strength isn't just how much stuff it's made of, but the absolute genius of its shape. A shape designed perfectly to conquer that invisible enemy.
So think about this for a second. When you bend a beam, the top part gets squeezed together and the bottom part gets stretched out. With all that pushing and pulling, what's stopping all those internal layers from just shearing past each other? Why doesn't the whole thing just delaminate and fail? Well, that's the big question we're answering today.
To really get a feel for this, just imagine 2 wooden planks stacked on top of each other. If you bend them, you can see it clear as day. They slide. The top plank moves one way, the bottom moves the other. That sliding motion is exactly what wants to happen deep inside any solid beam. But of course, a solid beam isn't just a stack of loose planks. It's one single piece. And that's because there's an internal force, kind of like a super strong glue, holding all those layers together and fighting against that sliding. That force, spread out over the area, is what we call shear stress. It's the unsung hero keeping the beam in one piece.
Okay, so how do we actually calculate this internal glue force? Well, it all boils down to one classic and maybe slightly intimidating formula. But don't worry, we're going to decode it together piece by piece.
And here it is. Tau equals VQ over IB. Now, you might sometimes see that Q written as A bar. Don't let that throw you. They mean the exact same thing. This little equation is the key that unlocks the shear stress at any specific point inside a beam. So, let's crack this code.
First up is V, for shear force. This one's pretty straightforward. It's just the external force pushing up or down on the beam at the exact cross-section we're looking at. Think of it as the load that the internal shear stress has to stand up against. Next up, we have Q, the first moment of area. Okay, this is usually the trickiest part, but it's absolutely crucial. Imagine you take a horizontal slice through the beam where you want to measure the stress. Q is basically a measure of the leverage that the entire chunk of area above your slice has. The bigger that chunk is and the farther it is from the center, the more it wants to slide, which means a bigger Q.
Then there's I, the moment of inertia. This number is all about the beam's shape. It tells you how much that particular cross-section, whether it's a rectangle, a circle, or an I-beam, naturally resists being bent in the first place. You can think of it as a shape stiffness factor. A higher I means a beefier, stiffer beam.
And finally, the easy one. B is just the width. It's the physical thickness of the beam at the exact horizontal slice you're interested in. It's the amount of material that's actually there to resist the shear. Simple as that.
Okay, so we've got the formula. But here's where things get really fascinating. The shear stress isn't the same everywhere in the beam. Not even close. It changes dramatically depending on where you look, and its pattern is completely dictated by the shape of the beam's cross-section.
Just take a look at this. For a simple rectangle, the stress is 0 at the very top and very bottom. It makes sense, right? There's nothing above the top surface to slide against. It then builds up to a maximum right in the center, forming this nice, predictable curve. But then, look at the triangle. Whoa! The peak stress isn't in the middle at all. It's shifted. This just proves that shape changes everything.
This quote really hits the nail on the head. The stress varies quadratically. Now, that's just a mathy way of saying the relationship isn't a straight line. It's that curved, parabolic shape we just saw. So, the farther you move from the center, the faster the stress changes. It's a non-linear world inside that beam.
And this table right here, this is basically your cheat sheet. It sums it all up beautifully. For a rectangle, the peak stress is 1.5 times the average. For a circle, it's a bit less, about 1 1/3 times. And the triangle is back to 1.5 times the average, but remember, the peak is at the halfway height, not the geometric center. This is a fantastic reference.
All right, we've got the theory, we've decoded the formula, and we know just how much shape matters. So let's stop talking and start doing. Let's put all this knowledge to work and actually solve a problem.
So here's our challenge. We have a beam, it's got a load spread evenly across it, and we have a very specific mission. Find the shear stress at one exact point, 3 meters in from the end and 130 millimeters down from the top surface. So,
Step 1. Find V. This is just a standard statics calculation, figuring out the forces inside the beam. After running the numbers, we find that at our point of interest, the internal shear force is 16 kilonewtons. Awesome. That's the first piece of...
We just plug them right into the equation. The number that pops out is our answer, the exact shear stress at that one tiny point inside the beam. Mission accomplished.
Okay, we've been deep in formulas and calculations. Let's pull back and ask the big question. So what? Why does any of this actually matter in the real world?
if you only take away a few things, let it be these. Shear stress is that internal glue. It's always zero on the very top and bottom. It's usually highest near the middle for most common shapes. And the single most important thing, the shape of the beam is everything. Understanding this is what allows engineers to design things that don't develop nasty horizontal cracks and, suddenly fail. And this all leads to one final really interesting thought. We've been looking at simple rectangles and triangles, but when you look at actual construction, you see these incredibly efficient I-beams everywhere. How are those so perfectly designed to handle all these forces?
Well, the answer is pure design magic. An I-beam puts most of its material on the top and bottom to fight bending, and it uses that thin web in the middle to handle the shear stress, which, as we now know, is at its max right there in the center. It's all about putting material exactly where you need it and nowhere else. It's a true masterclass in efficiency.